All right, so let's start. Welcome back, everyone. My name is Pedro Cenci Dal Castel. This is Chemical Fields lecture about secretion and absorption. So we covered what are fields and diffusion and boundary conditions. And then we created the linear and the exponential field. Now we are prepared to start exploring secretion and absorption. Remember that the lecture is being recorded, live streamed, and will be distributed in YouTube and other platforms. So the learning objectives here are, first, know how to implement secretion and uptake in CC3D, and then start to think about modeling and model building, finally. So first, in the field equation, when you simply add something, so every time step you'll be adding something, this is a source of material. So there is material being added to the field. This has applications for secretion, excretion, and synthesis. There is also sink. Sink is the opposite of source. Sink is draining of the material from the field, which is basically a source with the negative sign. When you couple secretion to the diffusion equation with decay, so now we have all the three processes happening. We have diffusion, decay, and secretion. Something very interesting happens, which is the field, as the time goes on, the field tends to S over gamma, S being the rate of production and gamma being the decay. So if you run this in CompuCell, where you have, let's say, your medium secreting a certain field and also decaying in the field, you see that the field tends to the value of S over gamma. I can demonstrate that in the Q&A session if you're interested in exploring the mathematics more in depth, but it's not important for the exercises today. The decay constant determines how long it will take to reach that steady state. So the faster, the higher the decay constant, the faster the system reaches the steady state. We use sources to model secretion, excretion, exocytosis. I will quickly review what each one of them are. So exocytosis is a type of active transport of chemicals from inside out of the cell. Secretion can be active and can be also passive, can be mediated by exocytosis, and can also not be mediated by exocytosis. Secretion is the regulated release of substances from the cell. What was gamma again? Gamma is the decay constant, which we covered in the end of the last lecture. No problem. And excretion is the release of waste, elimination of waste. So secretion is regulated. So in response to something, the cell will produce and release a certain molecule. And excretion is elimination of waste product. Secretion in CompuCell is set with different, you have to consider different properties. So for example, you can set a secretion with a constant rate of secretion, which means every time step, your cell will add a certain value to the field. The same value will be added to the field. But you can also tell your cell to hold a constant value. So instead of adding to the field, your cell will be holding the field at a constant value. You also have to consider where, in respect to the cell, secretion occurs, and whether secretion just occurs when your cell is in contact with another cell. So here I show different locations of secretion in respect to the cell. Secretion can happen in all pixels of the cell, in the center, just in the border, in the outer border, and the inner border. They are not super relevant for most models, but you might choose one of them. The only thing you need to consider, to be careful with, is that secretion is per pixel, not per cell. So if you tell your cell to secrete 10 units of field per time, it's going to secrete 10 units of material in all pixels that you choose to secrete. So if you choose to secrete in all cell pixels will produce 10 units of material. If you tell it to secrete just in the center, you will produce just 10 units of material in the central pixel. Also, finally, the secretion by contact is when you only allow secretion to happen when your cell is in contact with some other cell. And in this case, I'm telling these gray cells to produce and release material when they are in contact with medium. The difference between constant rate of secretion and constant concentration is exactly what I said. In the constant rate, you're always adding the same number of material to the field. So as time goes on, this number goes up. So we can see the cell is secreting 10 units of material every time, and the chemical concentration is going up and up and up. If you tell the cell to hold the concentration at a certain level, and the level is 10, all cell pixels will have the value 10 associated. Yes, you can also define secretion in the absence of contact, Ramon, but it will require Python coding. So let's take a moment to locate both in Simulation Wizard where the secretion plugin can be found. So I will open my to edit here. You don't need to go through this, but you can do it if you want. So when you go next, next, and next, and arrive in the cell properties and behaviors, you will see the secretion box right over here. I will hit cancel now because that's just a demonstration. And you can also call your secretion plugin from the CC3D ML menu. This is, again, the code snippets that toEdit offers. So by going to CC3D ML plugins, you will find the secretion plugin down over here. So take a minute to locate that, and then I will proceed. No, secretion is the creation of material in the cell. Right, Julio? Is the creation. Yes. No, we are not hearing. It's just a minute to find where you can set this. What was the difference in secretion and constant secretion again? Okay, let me go back here. The constant rate of secretion means that the cell adds material to the field every time. And the constant concentration is that the cell holds the value at a constant value. No, Sharon. No, we are not continuing from the previous example. Okay, let me go forward. So this is where you find the secretion plugins. And in the steppables, you can also, using the code snippets, and let me show you guys how to do that. In CC3D Python menu, there is a menu called Secretion Uptake and Field Integrals. In this menu, you have all code snippets, all code blocks prepared and appropriately commented for your secretion setup. So using these commands, you can first, you need to call your secretion object by doing secretor equals, you could name this whatever you like, okay? So, but a certain variable secretor equals self.getField secretor, and then the name of the field. This is acquiring the secretor object, the secretion object. And then you can use a series of methods, for example, secrete inside cell, and then you specify what cell, and then you specify the rate of secretion. Then secrete inside cell at boundary, and then you specify the cell, and then you specify the rate. Secrete in the center of mass, specify cell and rate. Secrete inside cell and constant concentration, cell and rate. This one is not rate. This one would be the value that the cell holds. And then secrete outside cell at boundary, the cell and the rate. And finally, secrete outside cell at boundary on contact with. Then you specify the cell that is secreting, the rate of secretion, and what cell that cell needs to be in contact with to allow secretion. And you define a list of cells. So it could be in contact with many different cell types. Finally, these options here are very useful. Let me see the chat. So the consequences maintain. Yes. There are these options here, total field integral, that gives you the total amount of field in all space. So you don't need to integrate the field over all space to know how much material there are in general in your simulation, in your lattice. Yes, Liam. There is also the amount seen by cell, which is it's the integral, but just across the cell pixels. And also the total count of secretion by the cell. So this keeps track of how much field, how much material a certain cell has produced so far. So this is how they look like. Once you get the secretor object, you can use the methods total field integral, amount seen by cell, and to keep track of the total amount, you have to use a specific secretion function, which is your secretion function and then dot total amount, dot underscore amount. This tells your secretor plugin to keep track of how much material your cell produced. Yes, Yasmina. Now let's take a look at uptake and endocytosis. So in uptake is the absorption, and it's different from endocytosis. Endocytosis is the active transportation of material. So let me give you an example. When cells absorb, for example, bacteria, macrophages can absorb uptake bacteria and other pathogens. They do this by endocytosis or some kind of endocytosis. But cells also absorb oxygen, and cells do not use endocytosis to absorb oxygen. So they are different processes, okay? When we talk about uptake, we have to consider two things: the absorption rate and the maximum absorption rate. So for example, let's say a bacteria absorb about 10% of the glucose around it. Okay, that's fair, 10% of the sugar around it. But if you put that bacteria inside a sugar pot, a pot full of sugar, it's not going to absorb 10% of all that sugar. There is a limit. There is a saturation value for the endocytosis rate. And this comes with this, we can demonstrate that using this graph. So as concentration of the material goes up, your cell take up more and more, absorbs more and more. But after a certain concentration, for very high concentrations, your cell just absorbs a fixed amount of material. And the threshold between the two behaviors we call saturation. So it's the saturation between the saturation of absorption. And uptake doesn't require you to call a different plugin. It's the same secretion plugin. So if you the secretion plugin is what contains all absorption and release methods. Okay, so if you have the secretion plugin in your simulation, you can use secretion and uptake. Avishak?
Yeah, so I was wondering, why is uptake negative when C is less than C saturation?
It is negative because it's with respect to the field. You are losing material in your simulation.
I see. I see. And then why
Yes.
why is it negative S if it is greater than CSAT? Like,
Because we are assuming that for very high concentrations of material, the cell cannot take up that much material. There is a saturation, so it only uptake a certain amount of that material.
oh, okay. I see. Thank you.
All right. Okay, I will proceed. So exactly as Avishak mentioned, uptake is a negative value. So when you do uptake tracking, same way as you will do secretion tracking, using the total amount function, you will get a negative value. So when your cell is eating something, and you ask the cell, how much have you eaten? And the cell will say, I've eaten negative 100 material, because it's with respect to the field, not with respect to the cell. The field lost 100 material, units of material, to that cell. Okay? So when you are doing, for example, okay, my cell is eating something, and I will use that something as an energy. You have to use a negative sign to invert the number. So now we'll have about 15 minutes to build this simulation, which is the very simple case where one cell is secreting something and the other cell is absorbing something. And it creates this interesting pattern, which we call shadowing. I don't know, some people call it shadowing. I don't know if this is an official term. So this is the simulation we are going to build. So open your to edit and create two cells. I will do that with you. So here you will create a new project. So new project, open your to edit, and then go to CC3D project. CC3D project, new CC3D project. Click that, give it a name. So demo 2. Next. Give it a name and go next. I like to reduce the cell lattice, but you don't need to do that. I will reduce to make the simulation run faster. So I will reduce to 50 by 50. And then don't change anything else. And then go next. Here, add 2 cell types, cell A and cell B. Then I will go next. Chemical fields. We need a chemical field. So I will call this one oxygen. Oxygen. With diffusion solver Fe, and then hit add, the button add, hit add. So type the name and hit add. I will do it again. Oxygen and add. You should see your field name oxygen and the diffusion solver in the table. Now next, here we want the secretion, the secretion plugin. We also want the volume flex plugin.
And contact too.
Contact is not necessary because we will freeze the cell by setting a very, very high volume target volume.
But it's always better to set the contact as a there are a lot of things that you can do in CompuCell, but there's certain habits that will make your life easier. And so when you're going to have cells present at all, setting the contact and volume by default will make your life easier. We saw with Susan that if you don't set those, things become strange sometimes, and it can be confusing. And so it's not that you have to do it, but it's a little bit like training wheels on a bicycle. If you click those 2 boxes, you've got the training wheels on the bicycle to start with. Once you're more comfortable, then you can do more daring things on a unicycle.
Okay, I agree. So let's go ahead and check the contact box and then go next. Here we will ignore the secretion plugin, this window, because we are setting these configurations using Python, because that's the most optimized way of setting secretion. So ignore that and finish.
There was a question, you 1 cell type or 2 cell types?
2 cell types, 2 cell types. So in the slide, I'm saying create 2 cells, 2 cell types. Yes, 2 cell types could be the same, could be just one, but to facilitate our life, 2 different cell types, and that's it.
And someone asked you
Repeat all the things to tick on. Yeah, so the contact box, the volume flex box, and the secretion box. I will come here. So these are the boxes you need to be checking. Contact, volume, and secretion.
When I do so, I get a new window, which asks me for the secretion plugin, uniform, on contact, and so on. So what should I put in there?
Nothing. You just hit next and finish.
Okay, and why does this window then appear?
This is, it enables setting of secretion in XML, but Maciek, the developer, said that this setting is not optimized. So people should prefer setting it up in Python. So that's why, because we have a time limitation in the workshop, we focus on the preferential ways of setting it up.
Okay, thank you.
Yes, and as James is saying, there are actually 3 different ways to implement secretion in CompuCell. So now the next step, once you have the simulation set up, you should make your cell A secrete and your cell B uptake by using these commands here that you code in your step function. Other settings that you have to change are setting a very high lambda volume, like 10,000, 100,000, so that the cells, they stay still and they don't move. We are essentially freezing the cells by doing that. So I will go ahead and do that. If you have doubts on how increasing the target volume, the lambda volume, sorry, please look at me doing the exercise. Okay, so I have my simulation open into Edit. I will go to the XML file. I will find the volume plugin, in my case in line 28. And then here I have 2 options, the lambda volume and the target volume. I will then increase a lot the lambda volume, putting some like 4 or 5 zeros there, and save my file. How are you guys doing with it? Okay, I will repeat. So I am in the XML, I find the volume plugin and increase the lambda volume. I will go to the Python in a minute. Each get field secretor get a different instance of the secretor. Yes. So why increasing the lambda volume? So in the slide, set a high lambda volume so the cells stay still. Okay, so that's why we are increasing the lambda volume so that the cells do not move. They stay still.
Why didn't we just fix the cells when we created them? Yeah, Sharon is asking.
Yes, we have to specify that somehow.
Naja, but when we create the cells, there's the freeze option. At least this is what I understood. So why didn't we just hit that button?
It's another way.
Ah, yeah, okay.
Yeah.
So alternative.
Yes.
I see.
Yes. So we already froze the cells before. So we take the opportunity to show people another way to freeze the cells in case they do not want to actually have a frozen cell. And then you can change the fact that the cell is frozen or not interactively on the fly during as the simulation runs. So this is another option. They have both pros and cons. But good observation. So now that I have my cells essentially frozen, I will go to my step function in the steppables.py file, and I will code exactly how that is being how that is written in the slide, but I will use here the code snippets to be faster. So if you have doubts on how to do it, please take a moment and look at me. I will do it for you. So let's say I don't have anything, and I know, okay, I need to set my diffusion, my secretion and uptake by cell types. So I go to CC3D project, then CC3D Python, and then I have a visit, and then I will visit all cells of given type. So by doing this and eliminating the junk, I get for cell in self dot cell list by type. This is exactly what I have here, for cell in self dot cell list by type. And here I will specify the type name of the cell. To get the type name of the cell, you have to type self dot and then the type name with uppercase letters. The numbers are secretion rates or absorption rates. Okay, so now that I already have these for loops, I will copy it to have another for loop over the other cell type. So here, the other cell type, I have to go self dot, and then the name of the other cell type with, again, all uppercase letters. I'll give it a space here. And now I will call from my to-edit snippets the secretor object. So I will come here, CC3D Python, secretion uptake and field integrals, and I will get here a secrete inside cell, a simple one. So this line is getting the object. I have to specify the name of the field, and it has to be, it cannot be misspelled. And you need to set the correct upper and lowercase letters. So in my case, the name of my field is exactly uppercase O and Casijan with lowercase letters. So that's exactly what I have here. I saw, for example, that some people set oxygen with lowercase o. Make sure your O is lowercase. So now that I have my secretor object, I will tell one of the cells to secrete, and with a certain secretion rate. Make sure you ident things. So when you put them inside your for loop, you need this space, which you can do by pressing tab. So secreting inside cell, I already have one of my cells secreting. Now I will make sure my other cell is taking up. What is the snippet called? Secretion. It's called secretion, and then secrete inside cell.
Yeah, so that's, I think the question was, you've got a lot of options here. Amount seen by cell doesn't actually take the chemical out of the field. It just measures how much is present. Secrete inside cell secretes at every voxel inside the cell. Secrete inside cell at the boundary secretes just in the voxels right inside the surface of the cell. Secrete inside cell at boundary on contact with is for polarized cells like epithelial cells, where you secrete, for example, from the apical surface only into the medium. So there are a whole bunch of options here, some of which you'll play with, some of which you can look in the manual to see the details.
Yeah. There is detailed documentation on that. So please feel free to access the documentation. The link is on the slides too. So now for my other cell, I'll go ahead and do the same thing. So CC3D Python, secretion uptake, and then uptake inside cell. So very simple. Here I got my secretor. I already have my secretor object, so I don't need to load it again. So I will delete it and specify my uptake. So for the purpose of the exercise, I set the first one, which is the saturation uptake, to 10. as it is showing in the slides, and the relative uptake to 0.1 as it's shown in the slides.
Can you show the pull-down menu for visit cells and show the options? Explain the options, please.
Okay, so in visit, you have for loops that access all objects of the ones in this list. For example, all cells in the lattice, all cells of a certain type, all clusters that we are going to cover in the upcoming lectures, all clusters of cells and cells within clusters, all lattice pixels, the neighbors of a cell, the boundary pixels of a cell, all the cell pixels, and the cells inside the cluster. Here, I am choosing cells of a given type. Relative means proportional. So when you have, so relative is the quantity of material you have times the rate. This is the relative. Absolute is just a rate. Oh, I typed this too. Relative is this, and absolute is this. Yes. Relative, you take up a fraction of the available chemical, and absolute, you take a fixed amount. No, Jupiter, no. Just the instructions in the slides. So now, after you have that, you need to build this pattern, which is one cell is on the left or on the right, it doesn't matter. And the other cell is a little bit further away, so you can create the shadow pattern. So in order to do that, you have to design your cell layout in the XML. So when you go down here and you see the region where you create your cells, Gilberto covered this in his lecture, so I will go over this a little bit quicker. So I will want two regions of cells, one region at for example, x equals 10, going to x equals 20, and then y from 10 to 20. And then the other one, I will do 30 to 40 because I want the cells further away from each other. So 30 to 40 and 30 to 40. And in the first region, I want cell A, and in the second region, I want cell B. The width of the cells, because I just want one cell, it has to be the same as the size of the box. So here I'm going to set the width 10. And the simulation is good to go. I will run this to make sure I got it right because I'm not sure. Okay, the cells are frozen. Oh, look at that. I didn't change my boundary conditions. So this is not right. So what I'm going to do now is change all boundary conditions to constant derivative 0, that you should have that by default. And set them 0, constant derivative 0, because I want the borders to act as walls, hard walls. Now I'm going back to the simulation and I will run this again. It is super, super slow. So what I'm going to do here is increasing the diffusion constant so that it's faster and we can see better the output. And by changing the diffusion constant, I change the profile. So let me set to maybe 0.1 again. And this is our shadowing demonstration. The boundary conditions are constant derivative 0, all of them. So you should have that by default in your code. I will give you guys 5 minutes. And you can also download the code from Good Jupyter. Fantastic. You can also download the demonstration in the students' materials folder in Google Drive. So if your code is messy, go ahead and download that from students' materials. Why don't I show both? So these are my boundary conditions and the cell layout, the initial cell layout. Hayden, are you there?
He had to step away for a second. What's up?
I was going to ask him if he wants to divide people in groups for the next exercise.
We can do that, but let's assign the exercise and then
Okay.
talk it over. We can ask people if they'd like to do this as a group, in small groups. We have enough breakout rooms that we can do that. So why don't you go ahead and, well, for this one, let's finish this.
Yeah, let us give like 3 more minutes for people to catch up, and because I think this is important, and then we'll go to the next exercise. We still have time. We have like 30 minutes, which is enough for the next one.
There was a question about going in Twidit menu to add a cell. Can we do that together? Maybe, Pedro, if you go to the XML
Sure.
and scroll up to where the cell types are defined.
Oh, yeah.
You can edit the XML by hand always. It's a little bit more work, but you can always do it. You have a cell type list here. If you wanted to add a cell type, you could copy line 25. Copy line 25. And then paste it in again. And you'd have to change type ID to 3. And give it and you have to type cell type ID to 3. Now you'll have to add that then to the volume and the contact as well.
Yeah, the way I like to do it is using the snippets. So you come here, you go yeah, no, that's how you have to do. You have to set up the cell type by hand, and then you can reset the contact energy by using the code snippets. Let's take a look at Katrin. Syntax error expected. So yes, after your for loop, you need a comma. Look at mine here. For loop always ends with a comma.
Colon.
Colon. Yeah, comma is this one. Colon is colon. Okay, easy to remember because I can imagine a column of points.
I
Sorry?
did that, and that's it?
Yeah, it should be it. Yes.
Mhm, mhm.
Does it run? Is it correct?
Moment.
Column. Okay. Column.
Still an error message, but I at least have 2 cells, but not what I expected, actually.
What's
Very
the
fun.
error this time?
What?
What error are you getting now?
No, I can show you if you want.
Sure, if you like, for a second. While people are working on this, why don't we let Katrine screen share for a second?
Pedro,
Yeah,
you
sure.
have to.
Sorry.
Yeah, this is what I got.
Okay. Secretor is not defined. Okay. So that suggests, okay, let's go back to your XML. I mean, sorry, your Python code
Yeah, your steppables.
and your steppable. Maybe make it a little bigger so we can see it.
Mhm.
Okay.
Okay, yes, I already know the problem. I will paste in the chat what we were missing. So this thing that I pasted on the chat, you need that in line 21.
So
You
so
need
let's
to grab.
so why don't we so why don't we just do this? Let's go to line 21 and let's pull down the CC3D Python code snippets. And we're going to go to secretion. And we'll go to secrete inside a cell, which says with secrete inside, which one are we doing? Secrete inside cell. So, okay, click that. Okay, and you'll notice that the first thing you need is secretor equals self.get field secretor. So you need to have that. So you need to type the name of the field in line 24. You need to replace field name with whatever you called your field. And it has to be exactly, if the capitalization has to be right. Now, then you can get rid of line 25 because that you're doing.
I'm looking for how I wrote the oxygen.
That's correct.
Lowercase, so you have to make it lowercase.
That's correct.
So.
Get rid of 25.
On 25, you have to get rid of. Commented is fine. Now it'll work.
Yes, it should run now. Let's see. No,
but
now if you had multiple chemical fields, you would have to define a different secretor for each field. So you might say secretor 1, secretor 2, secretor 3.
Now change visualization to field, to the oxygen field in the player.
Yeah. Okay.
Let's see. Same problem as before, not diffusing.
Can we see? Can you make the graphics window bigger?
I have to stop it for a moment and then. So this is how it looks like. And I don't get a dot, not even a dot this time.
It is secreting. You can see the total amount is changing, so it is secreting. If you look in the top where your cursor is, the red, so you notice the number is going up. So it is secreting. Yes, it is secreting, but it's not diffusing. So the issue is that diffusion is not happening. So the problem is not in the secretor, it's in the chemical field diffusion. It's in the diffusion solver.
Yeah, there is some problem. It's the same problem as before. I think she should download the demo from the drive folder.
Did you say that the diffusion solver worked when you did the demo?
Yes, the time before it was diffusing, but
okay,
now
you have the code. You have that code. Can you switch to the demonstration code? Okay. Let's look at the XML for that. Okay, let's scroll down to where the diffusion is defined. And just copy all lines 54 down to the end of the diffusion solver. All the way down. There, perfect. Copy that. Okay, and now we want to replace it here. And the one thing we're going to have to do is we're going to have to change the name of the oxygen from capital O to small lowercase o. You have to change it there and in line 66.
The one below.
Okay,
And also
now
your boundary conditions.
well, let's leave it. Let's not change two things. So let's hit save all. And now let's hit run. Make sure it works.
It's crashing all the time. I'm really sorry.
No, well, that's not your fault. The problem, see, what did we do wrong? Where did we put it? Did we somehow paste this in the wrong place?
The initial concentration expression might not be there. It can be commented out, I guess.
Yeah, something went wrong in the XML.
Unknown cell type, cell A. Mm-hmm.
Where did we put it? Let's see. Oh, because you have diffusion. Get rid of line 71 and 73, 72 and 73. And also lines 81 and 82. You're referencing a cell type that doesn't exist. Okay. Now, say. Hit play. Okay, good. So now that's working. So now we need to turn the initial values to 0. So now we're going to go back in initial concentration and set it to 0.
No. Boundary, no? Boundary?
No, initial values.
Yeah, the boundary should be enough. The initial concentration doesn't matter.
So let's go to line 70, and type 0,0 there.
Here, instead of
we're only going to have the cells secrete. We're not going to start with any chemical coming from the okay, good. Now save that and run it. Always change one thing at a time. Especially when there's a okay. So it didn't reload. Hit stop. Hit stop.
I think she
Run
didn't save.
and hit run.
Moment. It was not saved. Okay, so try again.
Again, I don't know how to say this enough. When you hit save, there are 3 save options. Always use the one on the right. That one, always. Okay, good. Now try it. Okay, now, why is it not showing diffusion when we turned off the... Huh, that is interesting.
Naja, anyway, I don't want to stop the show. I will download the code from Pedro and then we will finish the session.
After the
Thank you
lecture,
anyway.
after the lecture we can take a better look, but yes, we have to keep going.
So okay, I think I know what's happening, but yes, let's do that one-on-one. Okay.
Okay, I'll share my screen back, and if you guys need help, please stay for the Q&A and we can go over it one by one. Now, finally, I want all of you guys to pause a second and pay attention, and let's discuss together about modeling finally. So we've been doing exercises and exploring simulations, but and saying things as if we knew what they were. So for example, model. What is model? And if you do a quick search in Google, model means imitation. which I like a lot already. I think the word imitation is a very general, broad, and useful word to describe what model is. So, for example, this imitation of a building is a model of the building. It doesn't do anything, but it's a model nonetheless. What I like, how I like to describe model or to define model is a certain this representation of reality. So there is something out there, which is reality, that we try to communicate with via measurements, and we represent that. So we create an analogy, an abstract analogy. And the example I came with is the representation of things using numbers and addition and equal signs. So when you take two things plus one thing and it becomes three, we are representing this abstractly using numbers. So there is something real happening that we communicate via measurements, and we abstract that with symbols, with simulations, with diagrams. To define a model, we need to first define what are the things we're going to model, the objects, medium, cells, fields, networks, and what they do as individuals, their behaviors. They grow, they die, they migrate, they diffuse, and the interactions. So when one object and another object do something together, and there is an emergent behavior from the combination of two or more objects, for example, repulsion, adhesion, signaling. How do these things change in time? The dynamics and the events. For example, the isotropic diffusion equation is how the diffusion happens. A linear growth is how growth happens. And asymmetric division is how the division happens. Also, we have to care about the initial and boundary conditions. So for example, we have our yellow guy. Our yellow guy is the object. He has a behavior, he runs. He interacts by giving handshakes to people. And his dynamics and events are probably given by biology. And he has an initial condition. For example, he was born in Brazil. But let's try to give a definition for this concept. So for example, objects are carriers of properties and behaviors. The behaviors are the actions of these objects, and the interactions are the emergent behaviors from two or more objects combined. The dynamics and events are the way how actions take place in space and in time. Now we will explore, using these concepts, how we would structure the model we were working with in the previous exercise. So in the previous exercise, we had the shading demonstration, where one cell is secreting something and the other cell is absorbing that something. So the objects of this simulation of this model are medium, cell A, cell B, and the field. There are interactions. For example, cell A secretes the field. So we see we have two different objects, which are cell A and field, and they interact via the secretion process. Cell B absorbs field. Another interaction. Behaviors. For example, the fact that our cells are inert, this is a behavior that the object cell carries. Or for example, the field which diffuses. This is a behavior of the field. And there are dynamics. For example, the isotropic diffusion equation, the constant rate of secretion, and the relative absorption with saturation of the cell with uptake. These are how things are playing out in time and in space. Is that all intuitive for you guys? Or do you disagree with something? Me personally, I do not fully agree with everything I've put here, so you could also not agree. What would be the emergent behavior here in this example? Cell A secreting field. It's a behavior that only exists because both cell A and field exist. Is that clear, Gopal? So it emerges from the combination of these two objects. If you have just cell A, there's no secretion. If you have just field, there is no secretion. You need both. All right, so now there is a modeling exercise for you. And in this modeling exercise, we imagine something. We imagine a system, okay? A system that has space, has time, has players, agents. And I am imagining a system here, or better, an ecosystem containing two types of bacteria. One of the bacterium gets its food from the environment, while the other bacterium consumes the waste produced by the first one. Bacteria proliferate and die depending on their access to food. Now, give us the structure of this model. You can do that by typing in the chat. So what are the objects? What are the behaviors? And what are the interactions? Let's start with the objects. So I saw that Julio quickly deleted his message, but he started right. You had a good start there, Julio. So let me see.
That's supposed to be shift enter, not enter.
Oh. Mm-hmm. 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 So far, Sharon got it correct. Medium is also an object. Medium is also an object. Odame, A and B, medium, nutrient, waste. Perfect. That's it. Avishak, correct. Now, the behaviors. I want to see behaviors now. No one is talking about the fact that cells grow. They proliferate, right? Isn't that a behavior? Yeah. Good. Now let me see interactions. Now you'll see that you made a mistake. Give us interactions now. What happens to bacteria B after death? I don't know. I don't know. Maybe, I don't know, in religion you may find an answer. Do fields diffuse or just sit there like broccoli? Good answer. Good question, sir. Good question. I mean, they should diffuse, otherwise cells will maybe not have access, or they should migrate to get access. So interesting. Why broccoli? You know, the reason why I put broccoli is because it was an easy to find figure to represent a nutrient. Broccoli diffusion. Yes. Broccoli is expensive here in the US. I would love if they could be diffusing through my door. So what are the interactions? Catherine?
Oh, sorry, I was just laughing because of Sharon's joke.
I love broccolis. I have to show Sharon special way to cooking broccolis. Broccoli, I should say, broccoli. You just put it in the microwave for 5 minutes. The full broccoli. You just wash it and put it in the microwave. You don't need to cut it.
And after that, throw it away or what?
Season it with salt and olive oil.
Okay.
Yeah, so interactions here require one or more objects, sorry, two or more objects. When you said previously that secretion was a behavior, it was actually an interaction. You require the two objects to secretion. You require the cell and the field. So secretion, consumption, absorption, so on and so forth are interactions. So this is how I would build it, how I would structure it. I have the objects medium, bacteria AB, nutrient field, and waste field. And I have the following interactions. Medium replenishes nutrient. Bacteria A consumes nutrient. Bacteria A releases waste. Bacteria B consumes waste and does not consume nutrient. And also zero surface tension between all cells, neutral contact. Why am I doing this? Because nothing was said about the interaction in terms of adhesion between the cells. So I am assuming that they do not interact via adhesion. Yes, medium cell contacts are also interactions, which I am describing here by saying zero surface tension between cells. Now the behaviors, growth, division, based on their access to food, and death when they don't access food. Also waste and nutrient, diffuse and decay. For interactions, Julio, yes. You have a combination of all I should say ij greater than I objects. Ij greater than I objects. Or it should be ij I. Because you can also have interactions between cells of the same type, objects of the same type. All right, so next step is build a pseudocode that implements this model. Why include medium if nutrients exist? Where do the nutrients exist, Rama? Where? Where do nutrients exist? Where? The Petri dish contains what? Medium? They are in the medium. What is the medium? The medium is an object. Why not? What is medium then? A behavior? A dynamics? An interaction? Medium is an interaction? No, medium is a thing, is an object. It's something that carries properties. Medium has properties. Is a carrier of properties. It's an object. So pseudocode, as Kimberly asked, pseudocode is a simplified, arbitrary spoken language for designing algorithms. Yes, they are in the medium, Yasmin. And a pseudocode example is, I'm giving here, you just write with spoken language how you think those dynamics and those interactions should play out, in how they would be in the step function of our steppables. So for example, pick a number, start process. What is the process? User enters a number B, and then you test. If B equals A, break process. If B and A are different, you say you are wrong, try again and repeat process. And then when you break the process, you say, congratulations, you won the game. So this little game wrote with a pseudocode is an example. So you have to, yes, it's a halfway between English and Python. That's quite a good way of explaining it. And use a pseudocode, elaborate a pseudocode to implement this ecosystem in Python. Sorry, in the steppables of CompuCell 3D simulation. I will give you a few minutes. So Rama, if you guys want, if you think, oh, this is super easy, let me already build a simulation. Go ahead, build a simulation. Build a simulation, write the code. Go through the wizard, to edit wizard and build a simulation, no problem in that. But I think it's very hard, okay? So for this exercise, it's just a pseudocode, it's an outline of the simulation, not the actual simulation, because we don't have enough time to do it. But if you are confident, go ahead, I incentivize you. Avishek.
Yeah, so over here, the medium is acting like a source, right?
Yes.
Nutrient source. So A will have a uptake behavior and a secretion behavior separately. And depending on the secretion amount from A, bacteria B will have an uptake behavior based on the secretion amount of A.
Yes.
Is that okay?
Well, not quite. One thing to think about, and this is a fundamental principle of modeling, is you can make cells do things. But whether those, you should always ask the question, are the things that you're asking your cells to do things that they could do biologically? And one fundamental principle in biology is that cells only have local information. They know their internal state, and they know what they're experiencing locally. So they know what the local chemical concentration is, but they don't know that there's something secreting chemical somewhere else. And it may seem like just terminology, but the cell can respond to can take up the chemical in its local environment, but it can't know that some other cell is secreting it. It could know, for example, if it's in contact, physical contact with another cell. If it sends out filopodia and the filopodia touch another cell, well, then they can explore some distance. But fundamentally, cells have a surface, and they don't have vision. They can't see things at a long distance. So really, they can only experience their local environment. That doesn't mean that there can't be long-distance signals. If there's stresses in the extracellular matrix, for example, those can be transmitted a long distance. But the cell will respond to the stress at its local position. And so when you're designing a model or writing out these pseudocode or these conceptual models, it's important to ask the question, is this something a cell could do potentially? In other words, an expression I like to use is that there are no roadmaps in biology. There's no design plan for a human being. The cells in your tissue have to build the tissue knowing only what their local information is. That means the design principles in biology are quite different, and the way biological systems build themselves and maintain themselves and fail is quite different from human engineered systems. Things have to be done from the inside out. And so it's okay to put training wheels on and say, I'm going to say the cell does this. But it's always worth asking the question, could that really happen biologically? Or how could that be implemented given what is possible biologically? And so I think you brought up a very good question when you said that.
Okay. Thank you. Thank you.
And I shared in the chat a link to a template you could use to fill out for building models. You'll see that there are some things that are filled in. Those are just examples to help you think about the kinds of things you might use. Those aren't the ones that are relevant to this particular problem.
So Sharon, I read your pseudocode. You have to say, for example, what happens when the cell eats something? Do you reduce that amount from the field? Do the cells grow because they eat something? They've eaten something? There are a lot of interactions, ifs that there should be in the pseudocode. Okay, and also die. How do they die? What is the condition that kills the cells? Energy used. I like this. Look, Vikram is using energy. I like that. So when the cell absorbs something, that something becomes energy. And then energy gets used, right? And then cell die. I mean, yeah, it's not a decent pseudocode, because if I read this pseudocode as a code, my cells would absorb a nutrient, grow, secrete waste, proliferate, energy used, and then die. There's no condition for dying. Nothing is being said, like what happens with this nutrient, you know. It's an incomplete pseudocode. Yes, it's up to you to decide how much detail you want. But I think combining different ideas that I'm seeing here in in the chat, you could actually build a real pseudocode there. Waste secretion amount has to depend on nutrient uptake amount. Exactly. Sharon got it right. Waste comes from what? You consume nutrients, and then the amount of waste you secrete is probably proportional to the amount of nutrient you took in. Oh my God, my simulation is still running. I'm toasting my computer. Okay, here. Must partition its nutrient uptake. The more that goes into growth, the less that gets secreted. Interesting. That's another level of complexity. That's not really how it works in biology. Yeah. Medium secretes nutrients at a constant rate. Yes. Yes, Yasmin. Yes. Good observation. Bacteria absorbs medium. Yes. Good. Good descriptions. I'm seeing good description. Let's see, Julio. Julio came up with something that looks more like a pseudocode. Broccoli field, perfect. Uptake broccoli. So see, 4 cells of type A, uptake field broccoli, perfect. Transform part of the field taken up. Julio, let me teach you English now. Taken up. I had to be taught that also, so I feel your pain. Secrete the rest as field waste. Good. Or it could also store, couldn't it, Julio? It could also store energy. So then you start to see more complexity, because if you suddenly take this cell out of the field, it will still survive for a while. Why? Because it can store energy. And then for cells in back B, uptake field waste, perfect, and transform field taken up into volume. That's amazing. Fantastic. I think you guys had a good idea of what I mean here. So I will go ahead and present you my possibility of a pseudocode. So this is how I set it up. And this is what is actually implemented in a real simulation that you can download and run. So I start with a loop over all cells. And then I test if the cell has no energy left. If that is true, I kill the cell. Then I test if the cell type is A. Then I test if the cell is not full of energy, if it's not at capacity. If it's not at capacity, it takes up the nutrient. It increments the cell energy, so I'm tracking the cell energy for every cell, and then it releases waste. Then I test if cell has energy. If it has energy, I grow the cell, and whatever happened, I decrease the energy, because I'm assuming everything, the cell, just by existing, it's decreasing its energy. Then I test if cell type is B. Then I test if cell is not full of energy again, take up waste, increment cell energy. Then I test if cell has energy. If it has, I grow the cell and decrease energy. Then if cell is double the original size, I divide the cell. So this is all I need in a pseudocode for our steppable simulation. And when I open the file, so I'm not sure if you still want to see this, I will open the file here to show you guys how it was set up in reality. The simulation is called Ecosystem. It's in the Drive folder. And you can see basically almost exactly the pseudocode I've written there. So I loop over all cells. There are some things different. For example, here I set a tracking field to track the energy for each cell. Then I test if the cell type is B. Then I have the cell dictionary containing the energy. I test if that's less than 1. 1 is my maximum energy capacity. And then I uptake waste and track the amount taken up. When I track the amount taken up, I can convert this into energy. So I increment the energy by negative waste. Why? Because the tracked amount of material taken up is always negative because it's with respect to the field, not with respect to the cell. Then I decrease the energy, the cells grow, the cells die. Where do the cells die? Somewhere here, yeah. So if energy is negative, so energy is depleted, I tell the cells to shrink to 0, and I set a very high lambda volume to make them shrink fast. So now I want to ask you guys, what do you expect as an output from this simulation? What do you expect it's going to happen here? So run the simulation in your head, in your brain, if you still have neurons left at this point. Okay, almost lunchtime. People are thinking about broccoli more than ecosystem.
So cell would gradually deplete, and the population of bacteria B will increase, but the rate of decrease in the population of A will depend on how much nutrient is initially available and what is the uptake rate. And what else? Yeah.
Do you expect some specific morphology?
What do you mean by specific morphology?
How do you expect the cells to dispose themselves in space after a long time? Geometry.
Oh, okay.
From the inside, like from the center?
Which ones?
Both of them, right?
In the center of what? In the center.
The cells would grow spherically outwards or circularly outwards, and the ones at the center would die first, right?
Will they? I don't know. Will they?
I feel like they will gradually disperse.
Okay.
I think the code misses something because the broccoli eats up all the medium after a while and doesn't produce anything back to the medium. So this is the limiting step. The less the nutrient production is the limiting step for everything, and this is missing in the code.
But is it? I mean, it could be, let's say it's soil, and let's say that there's an ample amount of nutrient in the soil for the consumption the species that are consuming the nutrient. Like, could it be almost considered infinite, given that soil is pretty, if it's soil resolute?
I am reducing the amount of nutrient from the medium. So when I do uptake the nutrient, this function is decreasing the amount of nutrient. So yes, it is a limiting factor. And the fact that nutrient is the limiting factor is being considered here in this line 51 when I do the uptake function.
No, we are talking about a medium which will get which will be returned as nutrient. So the medium is the limiting factor, because every step in your simulation you lose medium.
Yes, you're true. So in my pseudocode, I should have medium produces nutrient. That's what is missing in my
Yeah, and
pseudocode.
is used up. I mean, this is a cell culture dish.
I mean, that's the
that-
assumption, though. It doesn't have to be a cell culture
Yeah.
dish.
Yes,
It could be
exactly.
soil, in which case
yeah,
nutrient.
it's just a suggestion.
But yeah,
So-
that's
so-
good
So
consideration.
one thing that's an issue here perhaps is that the word medium is used differently in CompuCell from the way it would be used by an experimental biologist. In CompuCell, medium is the space around cells. In an experimental biology, you put a physical medium into a dish and you either replace it or you don't. And so in CompuCell, the chemical concentrations inside of the medium would be used up, but the medium itself could never be used up.
So
So the broccoli lives from air and love and produces nutrient without any limit.
Well, I'm not saying, well, that's something you have to decide. But
Okay.
I'm just trying to say that the word medium in CompuCell means the space which is not occupied by cells. Whether that medium in the CompuCell sense has a nutrient in it or not depends on the chemical fields that you've defined. And so you can't consume medium in CompuCell unless you have cells grow and take up more space.
It seems like the way to account for that would be nutrient synthesis, maybe not like depletion of medium. In your sense, you're saying the medium is going to be a constant space, like it doesn't get depleted in that sense, but nutrient concentration over time could be influenced.
Again, I'm just trying to say that the word medium biologically, if you put medium into a dish, then there's a physical object which is medium in the dish. In CompuCell, medium simply is any region of the cell lattice that doesn't have cells in it. And so those function similarly, but not identically. I just want to make sure that when we're talking about it, we use the term in the same way. I think
we have to adapt the languages. That's right.
I'm afraid we're going to have to wrap up now in a minute. But the conversation, I hope this was a stimulating set of ideas. Pedro, do you have final things you want to go over?
I want to show the simulation running, and that's it.
Go ahead, please.
Okay, so no one got it correctly, unfortunately. So this is the simulation. Here I have the initial setup. Let me show you guys. This is the nutrient field. So it's being replenished in the medium and it diffuses into the cells. And here I have cell A, which one is cell A here? If I maybe change the color. Okay, so cell A is outside, and what's going on here? We tend to see cell B on the inside. So it's kind of a cell sorting simulation. It recovers cell sorting because cell A wants access to medium, so it wants to stay on the outside, otherwise it's going to die. So the person that got super close to the final shape was Loic, but Loic said that B would be around A, so it's the opposite. It's the other way around. A is around B. So Loic almost got the gift card. So we already see segregation.
Can I have a question?
Go ahead.
The blue cells produce the waste for the orange cells, and I don't know how much waste they can produce, but obviously not more than they weigh themselves. So where's the limit?
So in my simulation, the way I did it was the amount of waste produced is proportional to the amount of nutrient they consumed.
So the orange produced the waste?
Yes, the orange
Ah,
produces
yeah.
the waste. Yes, here we
Ah,
are
yeah,
seeing the waste field now. So we can see that the orange cells are producing the waste field. And finally, we got the final morphology configuration where the B cells are on the inside and the red cells are on the outside. So the simulation, the spatial agent-based simulation, is predicting a morphology, is predicting a spatial pattern out of the model that we imagined before. So this is one of the uses of simulations. You come up with an idea, a mechanism, you have that in your mind, and then you can implement it and see what is the output of that. How does that play out in space and time? And that's it for this lecture. So if you are interested in this simulation, you can download it from the drive folder. Thank you very much for joining. I will now launch the poll and feel free to ask questions. And I will stay here for Q&A, and you are also free to go have lunch.